Good afternoon. So we have now arrived at the last session in what has been, I think, a really amazing symposium. So I'd like to introduce myself first of all. I'm Jessica Kogel, and I'm with the National Institute of Occupational Safety and Health. We're part of the CDC, and normally when I introduce myself, I get a lot of kind of confused stares because I'm a mineralogist, and people really don't understand why a mineralogist would be working for the CDC. But I think you'll hear more about that in this session from our two speakers, and actually it's already come up. We hire a lot of geologists and mineralogists. And so this session is Minerals and Industry, Evaluating the Real Impacts of Mineral Dusts on Human Health. And I kind of came up with a subtitle for this session, and I would like to call it When Science, Regulations, and Terminology Collide. So, and you'll understand that, I think, as you listen to the presentations. So, you know, we've talked about a lot of different things during this symposium, and you know, just even today, we've been to Mars, we've been into the deep subsurface, we've been into the body, and we're going to continue in that vein of the body. And we're going to talk about minerals and how minerals interact with the body, particularly in terms of dusts and respirable hazards. So this whole idea of health effects is something that MSA actually, as a field, I think really established. It was, I think, almost exactly 25 years ago. There was I guess it was a workshop that was in Nantucket, and I think some of you participated in that. And there was a proceedings that came out of that, and that's health effects of mineral dusts, and it was George Guthrie and Brooke Mossman that edited that. So at that time, I think the field really became established, and it's a really fascinating one, and I think there's been a lot of advancement in the science in some ways, and then in others, not much has advanced. And a lot of that is around some issues related to terminology and imprecise terminology. So both of our speakers are going to address that issue, and I would like to actually make an offer and maybe even a plea to this community of mineralogists that this is an area that you can really have a huge impact. And so I hope that we can stimulate some interest in it, and we would love to see more mineralogists working in this really vitally important area and getting involved in some of the policy around these big issues. So with that, I would like to introduce our two speakers. Our first speaker will be Ann Wiley. She's from the University of Maryland, and she'll be talking about what makes an amphibole asbestos, history and status of regulatory issues dealing with amphiboles. And then following Ann will be Matt Sanchez. He's with the R.J. Lee Group, and he's going to talk about mineral misidentification in connection to potential hazards of mineral dusts.
All right. I've been introduced already, and I thank Jessica Kogel for doing that. I'll just move on to the next slide. I would very much like to thank MSA. I'm reasonably young, and I can't express my gratitude. I've put my favorite RIM and RMG volumes up here, ones that I reference constantly in the work that I do. The work that I do, I guess I'd characterize as pretty much testing raw materials, primarily for asbestos, before they're used in various products that we use. In the past 3-4 years, I've been very much inundated and involved in a lot of the litigation revolving around these talc claims. And specific to what I do in these cases is I'm just trying to characterize what are actually in these powders. And so most of my examples are actually work done by others. I won't disclose them out of professional courtesy, but where just basic mineralogical principles have been violated and resulting in misidentification of particulate. I'm not going to focus on the morphology issues. I think Ann covered that greatly. I'm just really dealing with just identification of minerals, and this is very just basic level stuff to a mineralogist. I'd like to thank also one of the sponsors, Crystal Maker. A lot of the work we do here evaluating TEM data, especially the SAED, the diffraction data, we use Crystal Maker heavily in that. We also rely heavily upon the mineral structure databases maintained, like the RRUF has been mentioned numerous times. We've come across some odd, what I would consider odd, kind of mineralogical curiosities in some of the powders that we have tested. And those databases have been very helpful to get at crystal structures to be able to compare the SAD and make sure we're identifying correctly what is being observed. Wrong button, sorry. It's funny, the up button goes back, it's kind of counterintuitive for me here. So some of these have been mentioned, Aragonite. What we're really dealing here, I'm going to talk about primarily also amphiboles. This is where the most confusion exists. And it's also important as we start out the talk, I think, just to, Anne talked a little bit about she talked about the regulatory environment, how it has changed over time, but some of these older definitions are kind of still in place. Another component of this is, people doing this work on a routine basis are generally, they do not have any mineralogical backgrounds. A lot of them will be biologists. They go out and take 5-day training courses to learn how to use a polarizing light microscope. They go out and take 5-day training courses on how to use a TEM in order to identify the 5 types of asbestos that were used commercially. So most of these methods were written for a very constrained problem. What we've seen in the last 20 years is these methods that were designed for a very constrained environment being used in just the open system of the world. And there's kind of constantly these kind of flare-ups of misidentifications and what's really going on. Anne covered some of the definitions of asbestos, but it is important, what we're looking for are these asbestiform varieties. And regardless of the name, I think if you truly have that fiber, so that asbestiform amphibole, I think it should be treated as asbestos. It shouldn't be a name game, but it should be identifying the minerals correctly as part of it. So when you look at there's all sorts of standard procedures by the EPA and OSHA and MSHA and ASTM and ISO, all these different kind of standard setting bodies and some regulatory community bodies. All the methodologies have this mineral identification aspect, the determination whether or not it is asbestiform, and then this idea of how much is present. The techniques, which are typically those fiber countings, is really dealing with just trying to quantify how much is there. And if you're not doing your morphology right or you're not doing your mineral identification right, this is unimportant. And Anne talked to that, this idea of this EMP, or just simply anything that's, the shape of your thumb is somehow hazardous. But my talk, again, I think I've already said this, but I'm just going to focus on the mineral identification. I keep hitting the wrong button. All right, amphibole nomenclature. These are quotes taken from some of the nomenclature here, starting with Leakey in 1978 and co-authors. The idea in mineralogy is we find the amphiboles if we're going to characterize, their crystallization habit, their crystal habit. When they're asbestiform, we should denote that. What I see a lot, I'm speaking for myself, and I do testimony in courtrooms, is where, they'll find documents where some geologist has reported out tremolite in the general area of a given mine. That means there's tremolite asbestos. So there's a lot of just misrepresentation that happens. But again, the nomenclature is clear. We were supposed to describing what it is and how it crystallized, if it's followed. 1997, they kept that same language was used and referred to. I know some of the committee are here. I think I saw John Schumacher there. In Hawthorne, there really wasn't a mention of it, but I assume it's the same idea in the descriptions. For those of you who have never seen it, this is asbestos in the field. This is an asbestiform ferroactinolite in Virginia. It has a unique crystallization habit. Again, it's just readily separable. Under a PLM, that's what it can look like, very hair-like. You actually can see the strong curvature. You kind of smash it around on the slide and look at it. Again, you can see how much flexibility those natural fibers have. Geez. Not an age thing, just I'm in good company not being able to figure out the buttons. I'm happy to be there. So again, this is just an example of an amphibole 3:1. This is not asbestiform. This is not asbestos. You know, it's already countable, you could say, you could argue. As you break that same grain up under the microscope, again, this is under a PLM, you start seeing, you know, characteristic fracture patterns along the 110 cleavage. You keep grinding it, you just keep getting particles. So, you know, any time an amphibole is present and you're going to use somehow a 3:1, you're always going to get particles that could be misclassified as asbestos. That's just the reality of kind of what we have to deal with. And it is you know, it is used to advantage by certain members of various communities. I don't think I want to go too much into this. These are the kind of standard methods. Anne mentioned a lot of these. PLM is primarily used for bulk samples. TEM is primarily used for air samples. There is I consider a very great misconception that somehow TEM, because it can magnify things more, is somehow a better instrument to analyze like a bulk material for asbestos. So the increased resolution of the type of microscope is somehow confused with it's a better instrument. So, you know, spatial resolution doesn't necessarily mean it's going to be the best instrument for the specific problem. Also, we get into the transmission. Most of my talk will be about misuse of it. And I'm talk a little bit, just in passing at the end, about trying to incorporate some EBSD and SCM work to identify, you know, discrete particles in these ground powders. This is actually from that R93 method that Anne mentioned. This is what must be proven by a lab in order to report asbestos. They must see that asbestiform morphology as defined. They mentioned the colors. You have to measure refractive indices in multiple directions. This is all optical, old, you know, classic optic work, birefringence, extinction, characteristics, and sign of elongation. So this is going back to just some classic, you know, optic type-based work. So I'm going to go through a set of examples here and show just how these basic principles are not being done reliably in the asbestos analytical community. And before I go through all these, just keep in mind that some of these labs are labs that will do testing for somebody like the FDA or like for the EPA on some of these sites. And so there's always, you know, there's always a big question in my mind, you know, data integrity. What are they really seeing? What are they really doing? And I think that's a big problem. And my only hope here is that we get the mineral identification right. That's all I'm trying, like that is so key. And the role of the society, the role of the education, and what we can do for this is very critical to these issues. So what this is showing, this table is taken from the method. Most of these labs use a technique called dispersion staining to measure the refractive index. I don't know how many people are familiar with that. It's just using the same principles like the Becky lines of the dispersion and the visible. But you do a little bit of a masking and you can create these different colors. So if you have something like tremolite and a 1605 oil, the refractive index in that direction should be much higher, and it should give you like that gold color, yellow gold. In this orientation, this is a near match in the 1605 for tremolite. You know, again, it's the crystals laying on C. So these are the colors you're looking for in order to say that, okay, the composition could be consistent with the tremolite based on the refractive indices. So this is taken from a report which alleged, I like the language here, sorry, tremolite and enthopholite asbestos by dispersion staining. This is the particle in question. Now, as we know, the optical properties, these minerals are anisotropic, so they're different in different directions. The polarizer direction in this microscope is the east-west. So this crystal he's seeing, in a 1605 oil, he's seeing a match for the elongation, the C-axis, if that was an amphibole. And as you rotate it to then look at the perpendicular to the C-axis, he's now seeing something that has a higher, well, he's interpreting as a higher refractive index, but it's actually a lower refractive index. So the point of this is this cannot even be an amphibole. The refractive indices are wrong. The refractive indices of that particle are too low. It's most likely, you know, some kind of a low iron chloride particle. But again, it met a 3:1 aspect ratio, and they misinterpreted the dispersion staining colors. And there we go. We have a lawsuit against a talc manufacturer for having tremolite and enthopholite asbestos in their talc. It's just more, that's the color it should be. That's the color it should be. They got it backward. Anyway, mismeasured. This particular gentleman's been doing this for 30 years. That's his experience level. He said he's been doing it for 30 years. I've only been doing it for 15, so. This is another example. This is the example from TEM. Here's the particle. Again, it's elongated mineral particle, sure. Compositionally, could easily be a tremolite, calcium, magnesium, silicate. Anyway, they went in and have a, hard to say that's a zone axis diffraction pattern, but a lot of these things are just taking it, no manipulation of the particles, just taking whatever they see at zero tilt of these filter depositions of particulate. They went through and measured a couple directions, identified a couple HKLs, and they identified it as the 641 zone axis for enthopholite. I'm glad people get that. That's good. So enthopholite doesn't have calcium. It can't be. It can't be enthopholite. This particular lab only has crystal structure data to compare to for 5 minerals, and that's it. They can't even compare to talc. This actually is a tremolite particle. We went through and took their same measurements and using Crystal Maker just compared, trying to visually show why they're wrong other than the composition. But the correct index is the 311 for that specific orientation. This is another example. Again, we have another calcium magnesium silicate particle in this particular one. They're identifying it as tremolite. There's the diffraction pattern. Again, they don't do any indexing. They just take a picture and it diffracts electrons. Therefore, we're good to go. We went through and measured, trying to index it, actually measuring the directions, and then again with the help of Crystal Maker. The shortest spacing there is a 6.6 angstrom spacing. Monoclinic amphiboles don't have that spacing. Pyroxenes do. So again, indexing this based on the measurements and the data that was provided, it's a diopside solution of pyroxene. This is a fascinating one. As you can see, this was identified as enthopholite. For this particular sample, there was a lot of particles that looked like this that were observed. But for none of the samples had any EDS information provided in the report or electron diffraction data, but they're alleging enthopholite. So without any real proof other than you have definitely clearly a fibrous mineral happening here. Could be argued to be asbestiform, sure. Just more what this particle looks like. It was very large, so there's multiple fields of view you kind of stitched together to try to give you an idea of this is a very, very large kind of fiber bundle looking material. We had the opportunity to actually go and relocate that particle, on their scope at their lab. So we go through and we collect EDS information. No iron, just magnesium silicate. Could be enthopholite, could be talc, could be sepiolite. The list could be very long. We go to some areas of the fiber. These fibers that are clean, don't have overlapping talc. We try to take a diffraction pattern from the one on the left, no diffraction. Trying to do the SAD from the particle on the right, the split there, no diffraction. So we went up and down that whole particle, no diffraction. The other particles in that sample that had similar morphology, no diffraction. Again, not enthopholite. Most likely, we called it sepiolite, assuming it was a poorly crystalline material. Example, again, talc misidentified as enthopholite. This is going to get boring for you guys, I'm sorry, but I should say these examples are taken from 6 different scientists doing work. This isn't just from one person. This is across many different people, some of them at the same laboratories, but different people doing work. In this case, they did indexing, they said, but again, it's important to know that this is the same lab as an earlier example, just a different scientist there. They have no references to talc. They can't even take measurements of a diffraction pattern and then try to index it to talc. I don't know why. It's been 5 years. They still can't do it. They indexed this particular particle to a 213 enthopholite zone. So we were using Crystal Maker just to see what it would look like, try to see if it matches. And it clearly doesn't match, right? We take the same measurements, compare it to talc, and we get a very good fit for talc. Let me go back one. What ends up happening when they do try to index these things, they're just like forcing it to be enthopholite. So what they did is they they matched what they observed, this direction, with this direction. They matched it to, so they measured the two shortest vectors, right? The two shortest distances on the observed pattern, but then they indexed it to not the actual cell, that basic cell, or what you want to call it, those basic directions in the anthophyllite pattern, but they just made it fit. So I don't know how to explain this very good verbally, but they assumed a 10% error was okay on that measurement and just like made it fit without any other thought to it. They didn't check any other distances, any other spacings in order to make their alleged identification. This is an example of material from human tissue, somebody that had a disease. This is the particle that was given in the report. We had the opportunity to go in and relocate those particles and obtain our own data from those same particles because we could not make sense of their data enough to verify their findings. Again, you see right here, they identified it as ferroanthophyllite. So again, we were able to relocate it, a little bit of a tear of the filter. This was the original EDS that was given to us. This is actually the reference grunerite, or the amosite standard. Notice the manganese, they got manganese in here. You go through, they didn't do any zone axis analysis. This is the image they gave. We went in and obtained a nice zone axis pattern, indexed it to the bar 100 monoclinic grunerite. So again, you actually have bona fide asbestos fiber in this person being alleged to be ferroanthophyllite in order to sue a talc manufacturer. These are a little more interesting. I'm trying to get a little more complicated as I go through, or particles. This is identified as anthophyllite. Again, iron, magnesium, silicate. Here's the diffraction pattern. You go through and indexing it. You've got it. It's monoclinic. It's not orthorhombic, so it's coming tonight. And also likely some talc or some wide chain, error going on there. So we have some kind of an amphibole, some alteration also happening on this particular example. But again, all we have is this to work with. We can't go to other zones or tilt to explore it any further based on the data we have. Just to set up the next little bit, I'm running out of time. What I have here is, this is again with Crystal Maker, but we've got a sheet silicate. We're looking, C is up, B is to the right or the left, however you want to look at it. But we have what that diffraction pattern would look like for these three crystals. So we have talc coming tonight, a monoclinic double chain amphibole, right? We got a triple chain monoclinic for clinogym thompsonite. So we have very similar properties. One of the most fundamental things that go wrong with a lot of these routine asbestos testing laboratories is they use what they call the 5.3 row spacing to identify what's there. Meaning they just measure the distance between the rows as 5.3, and then they assume it's an amphibole. And that comes from the assumptions when you were doing in the assumed environment, or when you were doing like a clearance sample in a school where you had just removed asbestos. They weren't really concerned with, they already knew asbestos was there, so there were a bunch of shortcuts that were put into all these methodologies and in practice. And then those shortcuts get put into place when you expand these analyses out to the real world or into more complex systems. You get all sorts of errors like this. So in order to tell these three things apart, you've got to measure that B direction, right? That's a 4.5, that's a little over 9, and this is going to be 13.5 or something for that triple chain. A lot of times these things, and this, I'm not I don't think Dave Veblen's here, but these things are intergrown at very, very, very micro scales, nanoscales. We're looking at half micron sized particles. So a lot of times you get into these particles and you're seeing multiple phases present in the same particle. So as you start getting combinations of talc and cummingtonite, or talc and clinogym thompsonite, or chesterite, or gym thompsonites, you get different kind of intensities over the reflections, and you need to be mindful of these things. This is an example here. Here we got the particulate. This was argued to be a bundle of asbestos fibers. This is the EDS from the other laboratory. They did a dual zone axis analysis on this one, they said. So they took 2 pictures. They didn't index it. They just took 2 pictures. We also don't know they also didn't report or record what that interzonal angle was. Anyway, we move on to the first one. We go through, we index it. We get a nice solution for the 302 clinogym-thompsonite. Again, this is that B star direction. The 020 is measured at about 13, a little over 13 angstroms. Move on to the other one. We get the same thing. More importantly, if you notice on this one, we also get some of the systematic absences of the space group for clinogym-thompsonite in that orientation. I think I'm almost up. Some of these particles we see, especially when we start seeing these like clinogym-thompsonites in some of these talc samples from certain localities, you start getting some little nastier looking morphology. I mean, invariably when you're seeing these more nasty morphology, you would say more of, you know, this idea of maybe you do have that fibrillar splitting, that asbestiform nature. What we invariably find is we always find these clinogym-thompsonites or talcs in those locations. We look at the samples and the amphiboles from the same material on a larger scale. None of them have that habit. This is something that's only occurring in very small pieces as you go to high magnifications using TEM. I think I'm pretty much out of time. So here's another clinogym-thompsonite and talc particle of that one that looked pretty hairy. So it's not even an amphibole, at least there at the end, which shows a possible asbestiform character. You know, that same sample, this is an example of amphibole from there. These are the larger particles. The larger the particle gets, the easier it is to tell if it's asbestiform, how it crystallized, right? We're getting closer to how it crystallized in nature. Relatively high refractive indices. But again, even on these particles, we can see those little blobs there. Those are much lower index particles. So even these larger particles have you know, bits of talc stuck to them. Now, whether they go into them and they're coherent at this scale, I don't know. But when we see we see the smaller particles in the TEM, we see a lot of these coherent growths of talc and clinogym-thompsonite with these cummingtonites. And on a rare occasion, we've seen enthopholite, but it's never been outside the presence of the cummingtonite. It's always been as I don't know if it's exsolution or what the mechanism is exactly there. I'll just touch on this briefly. A lot of the work that we're doing is actually on the PLM side. We'll go in and I find the amphiboles, or what we suspect to be amphiboles. We pick them out. We then put them down to do EDS, SEM work on, and EBSD, just in order to get that you know, primary reason is optically, we don't know if these things are cummingtonites or actinolites. We can't, from the optics, we can't tell the composition. So by pulling them out, we're able to obtain that information. And then furthermore, with the EBSD work, we're able to get the crystal structure information to confirm that it's a monoclinic amphibole. Or in this particular case here, we believe we actually have a piece of chesterite from the EBSD. So the refractive indices of chesterite and these cummingtonites and they all overlap. So there's a lot of work that needs to be done. Well, again, we need to identify minerals correctly. So I hope that wasn't too boring for you guys, and also somewhat eye-opening on maybe what you read in the news and what some of these issues are. There's definitely a greater need in the industry for more mineralogists in these issues. I can't make any of that happen, of course. The industry has to step up. The regulatory bodies need much more influence from the mineralogical community to make sure they're identifying these particles right. I remember it was at Michael Cella's talk yesterday. We're doing this, this great nano characterization of these particles. And when we get into these issues, it's like we're so far from that. And we're really these communities are really far behind on this nanoparticle characterization. There's a great need there. Participation in these ASTM and ISO groups, though it's very painful due to the people you have to work with, it's very much needed because the pathway they're headed is not scientifically correct for the most part. And again, continued research. The more we understand of these particles, the best we can protect human health. And the more we understand is we actually know where to put our resources in order to protect people. And if we're wasting our time on this on other stuff, we're really ignoring those that really need the help and could use those resources. So anyway, I'll leave with that. Thank you.